Okay, welcome everyone. So this is RAD 1126, Chapter 10, Lecture 2, Electromagnetic Spectrum. What we'll be talking about today, of course, is the EM spectrum, but also a little bit about how we change the wavelength of our KV, what that all means, or we use KV to change the wavelength, I should say. We'll get into terms like intensity versus quality versus what the breakdown of MA in time does. Lots of good stuff. So I guess we'll get started. So you've probably all seen this before somewhere, this chart of electromagnetic radiation. And you can see there's different types. We have radio, microwave, infrared, visible light. And as you go from left to right, with gamma rays over to the right, you can see that the wavelength gets smaller or shorter as you go from left to right. The wavelength is defined as from the top of this amplitude to the next one, so like this distance here. Alternatively, I guess, if you drew a line down to the bottom of each one, so this bottom part's known as the trough, you could connect those and that would be the same thing. Right? But you can see that it gets shorter and shorter as you go to the right, meaning that shorter wavelengths equal more penetrating radiation. And in X-ray and gamma radiation, you're actually at a point that this is ionizing radiation and has the ability to knock out electrons in your tissues. We'll talk more about that next week. What we're going to talk mostly about today is what happens to create an actual X-ray photon, right? What happens with those electrons that come from the cathode, from the filament, and end up in our target, in our tungsten? What's actually happening in the tungsten atom? Before we get there, I want to talk about the third or fourth line on here called frequency. And I want to show you that as the wavelength gets shorter, the frequency actually also increases. The frequency is how many waves occur per unit time. It's kind of like if I'm standing under, infrared, and I'm just counting the waves go by me. If I wait like 5 minutes, I'm going to count a certain number of waves, right? But if I do the same thing over here, where I have a shorter wavelength, and I count another 5 minutes and actually see how many waves pass me, I'm going to have many, many more, right, in that same amount of time. That means it's a higher frequency. So if you like arrows for your notes, you could say as the wavelength decreases, is shorter, frequency increases. Do I care how big they are? Well, if you kind of look at X-rays, it's in that sort of atomic level, right? So they're really, really small. And that's why you need an awful lot of them to really get a radiograph. But they're not enough to kill you, at least not right away. And unless you use an awful lot, which our machines won't generate, right? Can't generate as much radiation as you would like sometimes. Gamma rays, though, will kill you. They create too many ionizations, and they're too strong. So radiation is not good for you, but most of the time you live, right, after your X-ray. Yeah, like if you don't fall off the table. I would say no one's ever died on the X-ray table, but that wouldn't be true. So, but, yeah. For the most part, your body has a very gifted or unique way of being able to fix itself. So despite all these ionizations that occur and knockouts of DNA, most times your cells are repairing, right? And you go on. So we can talk more about cellular damage next week, because today we talk about how the electron turns into a photon and what happens in the chunk of tungsten. Next week, I'm pretty sure we're going to talk about what happens when the photon interacts with an atom in U. Today, we're still in the tube, basically. So we said X-rays are the EM spectrum, electromagnetic spectrum, and that's going to make even more sense, especially when we talk about what happens in terms of Bremsstrahlung radiation, which we'll get to in a second. And we use them because they can penetrate stuff. They go through solid objects. They don't go very far, right? Because they interact with materials like you, they interact with the air. By the time you take an exposure in the room and you go into position the next view, there's no radiation anymore. You don't have to be afraid to go in. And X-rays don't travel very far. And they get weaker with the square of the distance, which we'll talk about in another class, what that exactly means. Now, if you're in outer space, X-rays go really far, because there's like nothing to hit. Like space is super empty, mostly. And in order to create X-ray photons, we said last week that you need a source of electrons. We said that you not only need a source of electrons, but they need to be accelerated, which is the kinetic energy. And in order to accelerate them, we have to juice them up, essentially, with thousands of volts. That's where the kV comes in, so that they can go all of about an inch from the filament to the cathode, to the anode. Excuse me. However, what you didn't know, unless you read up, anyone read the book on this chapter? Oh, good. The last class, like 2 people raised their hand. I don't know. We're starting to get worried already. If I'm standing, and imagine I could see the radiation coming out of the X-ray tube, which you can't, it's invisible. That would be really scary if you could see this. It's like good that you can't see. It's like beep, all you hear is a beep, and the patient could be like staring right at the tube and wouldn't see a thing. But there are 2 processes that can result in an electron creating a photon. The 2 processes are Bremsstrahlung and characteristic. Bremsstrahlung is a German term. It means breaking, and that'll make more sense when you see the pictures. And that's really the one we want to focus on the most, because at the energy levels that we use, the particular kV that we use, that type of process happens more often. Most of the photons are created through Bremsstrahlung versus characteristically. But when they come out, right? You can't really tell the difference. They all have different energy levels. So Bremsstrahlung is kind of cool because when you think of an interaction, you think of like something hitting something, or there is no real interaction in Bremsstrahlung. There is an electron that comes near the nucleus, gets caught in the electromagnetic force of the nucleus, because there's a charge associated with the nucleus, right? And it's stronger, that charge, the closer you are to the nucleus. But what happens is the electron coming in slows down and actually curves and changes direction, loses energy when it's slowing down. That loss of energy is transferred directly into an X-ray photon that pops out of the nucleus. Super cool. So it's kind of like if you started with an 80 keV electron, if it lost 20, right, 20 keV of energy as it slows down, you would be left with a 60 keV photon popping out. It looks like this. Did it touch the nucleus? It gets close. Boom. Okay, photon pops out. Kind of cool. And the closer you get to kind of, if you want to look at the nucleus as kind of like a bullseye, which if you play darts, it's kind of hard to get the dart right in the little red circle in the middle. It's much easier to hit the surrounding area. It works the same way. If it gets caught up closer to the nucleus, right, like this one does, and this is only happening 2% of the time. Because for an electron, this is a big, vast ocean. So to kind of make it here, right, means it will slow down a lot more, right? It's going to lose 20 keV. Right? So it goes in at 60, it loses 20 because it kind of hits this zone. And out comes a 40 keV photon. Another example up at the top is you have a starting electron with the same energy level, except it gets nowhere close to the center. It hits somewhere up in this zone, which happens much more frequently, 20% of the time versus 2%. But because of that, the energy level over here doesn't cause it to slow down much. Like it curves, but it still comes out with almost as much energy as it started with. It only lost, well, it lost what? 56 to 60. It lost 4 keV, so that's what your photon comes out. I kind of like this image though, also, because the 40 keV has a much shorter wavelength than the longer one. What you don't see here, because this image at the very beginning was kind of general, is technically the wavelengths in here, this is kind of like a range. But if we just talk about X-rays in general, when we change the keV, we have the potential of changing our wavelength, right? So when you increase the keV, the wavelength gets shorter. You can't turn an X-ray into a gamma ray, but you can make a shorter wavelength and make it a little bit stronger. So I like Bremsstrahlung. It gets caught up in, you know, that mysterious feeling you have when you take two magnets and you try to put them together and you feel that weirdness? Yeah. It's like one of the easiest things to do, but you don't have to buy major equipment to feel the magnetic force. That's what you're having in Bremsstrahlung. So Bremsstrahlung causes you to get lots of different potential energy levels, right? Because I only gave you like 2 examples here, at least the book gave you 2, but there's others. Essentially, the closer you get, the more energy you end up with. Some of them might have interactions way out here, basically cause nothing. And of course, we're throwing in quintillions of electrons. So I didn't mention it last week, but a quintillion is 1 with 30 zeros after it. This is like, I don't know, something like a trillion billion, I don't know, something huge, right? Now, I mentioned just a second ago that a lot of these photons that are generated don't end up with a lot of energy. So a few things can happen, right? Because they don't have a lot of energy, they don't even make it out of the X-ray tube. They just can't even get through the glass of a little window. Another possibility is they make it out of the X-ray tube and they become part of what's known as the primary beam. So anything after the X-ray, where the X-rays are coming out, is the primary beam. Then some of them might die before they actually hit you, just in the air. Don't even make it to you. And then some of them, my photon friends, some of them will hit the very tip of your skin, not really penetrate anything, but just get completely stuck in you, leading to just dose to the patient. So where do you think I am going with this? Title says filtration. What's filtration mean? Don't talk about X-ray. When you filter something, what are you doing? You're getting rid of something, right? Filter your water, go to Newark. Anyway, if we can get rid of some of the X-rays that do not contribute in any diagnostic way to the image, then we can reduce the dose and it's all good. So we have a system called filtration that consists of a way to get rid of some of these really, really long wavelengths. Remember, long goes with weak. The ones that will only contribute to the dose of the patient. So how do we do this? There's actually two ways that work together. You have filtration that's built into the tube already, just kind of like it was there anyway. Like the glass that I just mentioned in the tube that the photon didn't make it through the window. You could look at that as filtration. Or the oil that's in the tube. If there's something, or the collimator mirrors, if there's something that's just part of the tube that interacts with a photon and kills it, then that's considered inherent filtration. It's inherent. It's inherently part of the tube. It's like you built it and you happen to get some filtration along with the other stuff. Then you have added filtration. Added filtration is actually putting in a sheet of aluminum or copper and putting it in the way. Shorter wavelengths just go right through that. The weaker ones, between the inherent and the added filtration, die. There's a magic number that doesn't appear in this PowerPoint. We need to have 2.5 millimeters of aluminum equivalent filtration. 2.5 millimeters of aluminum equivalent filtration. Now, I need to explain that because it's not as intuitive. The combination of the mirror and all the inherent filtration, like the oil and the glass, combined with, let's say, maybe 1 millimeter of actual aluminum that's added, all that stuff is supposed to come out to 2.5 millimeters of aluminum equivalent filtration. So in X-ray, and you'll learn more about this in your protection class, you need a certain amount of concrete in the wall. How many feet of concrete? Well, I don't know exactly, but however many feet can be turned into a certain amount of aluminum equivalent, even though it's not aluminum. Why 2.5? Because if you go much higher, you start to kill the good photons, right? I mean, you don't want to stop them all. Yes?
So the added filtration, this is occurring within the tube, or is this at times now, like within the gear?
No, the added filtration is built into the collimator.
Okay.
Yeah, it's in the tube. It interacts with the photons before they get out of the tube fully. So, I mean, that works out with Bremsstrahlung, because in a Bremsstrahlung situation, and a caveat to that, when you're utilizing a pretty inefficient generator, like a single phase generator, you actually end up, for all the amount of radiation you put out there or set on your kV, you get about a third of what you set. So if you set 90 kV and you take the average energy of what's in the primary beam, you end up with 30 keV photons overall. So this means your primary beam that's coming out of the tube has a mixture of different energy level photons. So that means we can say that the beam as a whole is what's known as heterogeneous, different energy levels, sometimes known as polygenic. If it were all the same, which it's not, if it was all the same, it would be homogeneous. Now, when you set your kV, you're actually setting what's known as your kVp. Anyone know what the P stands for? What? You guys know? Potential? No, it's not peak. It is peak. Did you say that before? No. Okay, it's peak. So what that means, if you set 60 kV, the maximum you can get is 60 kV. You can't set 60 kV and get 68 kV photons. Right? So when we say kV, we leave the P off, but it's really there. Right? So if you said to me, Professor Lobel, what kVp do I need for the hand? I would give you the same answer as if you said what kV. Right? It's the same thing. Now, if you use a more efficient generator, you can get better results. And we'll talk about that near the end of the class.
Does the KVP imply that it can be 60, but not necessarily? It can
No.
be up to that amount, but not more, but can it be less?
Oh, it can definitely be less. Yeah, I mean.
And is there a lower limit that it can't be lower than?
Well,
Or
here's.
does that not matter?
Well, you get a lot of low level photons. So here's an example where you use 60. No matter what you do, you're never going to get more than 60. But you're definitely going to get a lot less. So here's only two examples, but you might be getting 59, 58, 2, 1. The further away you are, the lower it goes. Right? The closer you are, the higher. This is just an example of 2, but imagine there's like, I don't know, 28 billion, which is a low number. Right? Billion has how many zeros? 7 or something?
9.
9. What did we say about quintillion? Like 30? So. Right, so this is what we already said. We're throwing in lots and lots of electrons. Because for one, remember we said the process is inefficient. We only get like 0.5 or 0.6% X-rays, no matter how many electrons we send in. Mostly what we get is heat. But what does come out is a polyenergetic or heterogeneous beam. And like we said, if you set kV at 80, you're going to get 80 or less. With Bremsstrahlung, you're getting a whole lot of different things. With characteristic, things are a little different. First of all, it doesn't happen as often. Second of all, with characteristic radiation, the interaction is that an inner shell electron actually gets bumped out by your incoming electron that originated, if you remember, at the filament. And here, the actual X-ray photon energies that come out are based on the binding energies of the electron and depending on its orbit or shell is. So first of all, you need to knock the thing out. So if the electron doesn't hit anything and just goes flying through, guess what happens? Nothing happens. 2, if the electron hits an inner shell electron, but it doesn't have enough energy to knock it out, in other words, enough energy to release it from its binding energy, nothing happens. It might vibrate, and if it vibrates, it's known as excitation. And if that happens, which happens quite often, you get heat. So this is happening a lot, right? Because we said we're getting like 99% heat. You have to be over the binding energy, but not by much. So I know that's kind of weird. If you're way over the binding energy, quantum physics is weird, it says nothing happens. It's kind of like if I hit you with a bat in your head, you get a bump. But if I hit you too hard, you don't get a bump. Right? Doesn't seem to make sense. So you have to be over the binding energy, but not by much. It's not like as long as you're over the binding energy, you're good. Just a little bit more.
To get actual X-ray
To knock out an electron
out of this.
out of an inner shell. But hold on, let me just finish kind of the rest of it. So let's say your electron that's coming in interacts with an inner shell electron and knocks it out. So what happens? It gets knocked out. It can then go on to like do other things to other tungsten atoms. Right? So you might get multiple X-ray photons from that original electron. And 2, an inner shell electron will act, and again, this is a property of physics, that this inner shell, or any of the shells really, will want to fill the vacancy that was just created when that electron was knocked out. An outer shell electron will come in. When an outer electron moves in to take the place of the newly vacated inner electron, a photon is released. That photon energy, though, is very specifically related to the binding energy. You're going to see on the next slide that instead of getting a whole bunch of different potential X-ray photons, you get very specific numbers. So, for example, okay, this is a tungsten atom. Every atom has different binding energies. I'm only holding you to memorize tungsten. So when you look at this, make it a little bit bigger. Just get rid of that for a second. When you look at this, all right, you can see that the K shell is pegged with this number 69. The L shell is 12. Forget about the minus sign for now. The M shell is 3. N is 1. And then it really drops off to 0.01. Now, I should probably take these numbers and add them in here. Do I have a pen? I get that just right? No, thanks. We have 57, 66. 57, 66, 68, and 69. Okay. Can you still see the numbers? Okay. These numbers represent what happens when one of the K shells, one of the K shell electrons, there's only two of them, get knocked out and get replaced by one of the other shells. Okay? And you don't just get any energy level photon, you only get 57, 66, 68, or 69. So what happens is if we knock one of these out, we get 69. If it is replaced by a L, okay, we get 69 minus 12, which is 57. If we replace one of these with a 3, we get 66. If we replace with 1, we get 68. So we're getting a good amount here because there is a lot more potential energy in these outer shells as it falls down.
Good. And depending on what shell these electrons are actually dropping into is depending on the binding energy.
Right. So right now we're talking about replacing a K. If we lose something that's M and it's replaced by just an N, like right next to it, we don't get much at all.
Right.
Right? In that case, it would be like we'd get an energy level that was like 2. Right? Yeah, closer gives you a good starting number to work with, essentially. Okay? So in a tungsten atom, when X-rays are created characteristically, if it happens to be a K shell, you're only going to have those 4 possibilities of photon energies.
If we have it.
So the example here and the one that's in the book, this is, if you look at this, electrons falling from various outer shells, but into the K shell, not L, not O or N falling into L, but just for K. Just for K.
And they're speaking really about K because K is closer.
K has the, that's really the only one that matters. The other ones are going to result in lower level photons, and that's where, again, filtration may come into play. Now, interestingly enough, when X-rays are created, we said most of that ends up being excitation, a vibration. We don't actually knock out anything, and all we do is end up with heat. But also, of the X-rays that make it into the primary beam, most of those X-rays that hit you get stuck in you. Somewhere around 98% of the radiation gets stuck in you. This is terrible. So not only is it pretty inefficient in creating X-rays, mostly heat, But also, most of the X-rays get stuck in you. Yes.
Does Bremsstrahlung also produce heat?
His question was, does Bremsstrahlung also create heat? No. See, if we say a photon was created through a Bremsstrahlung process, that means it worked. And there was an actual slowdown. Right? So remember, we're throwing like, how many electrons with 30 zeros? So we have a lot of heat, but if a photon is created through Bremsstrahlung, you don't have to think of that particular one electron as causing like any heat. Right? It just slows down, and the amount that it slows down is transferred to an X-ray photon. That's Einstein, by the way. We conserve the energy. What's lost when it slows down is transferred into what gets picked up by the photon coming out. So now, 98% of radiation gets stuck in you. But we can try to reduce that. Right? We can try to get closer to 1% than 2%. It doesn't sound like a lot, but better. Right? If we use higher kV, you have a better chance of more photons making it through you and hitting the image receptor. But it turns out, and I should have said this in the last class, it turns out that the majority of the image is based on radiation that gets stuck in you than radiation that actually makes it and interacts with the image receptor.
So it's better if it gets stuck in you?
In a weird way, yes. Okay. So we're going to pick that up a little bit more, but we know we have a lot of heat, and we said this is because of this excitation process. And sometimes it actually even releases some infrared radiation. That's inside of it, so we don't care. Infrared is heat, right? You go to Burger King, right? They have those like hot lights, like infrared. Go to the suntan place. I used to do that. I probably wouldn't now, with like all the news about like skin cancer and stuff. Okay, so there's some stuff that we talked about last week. That's why, like on the test, I might have something like this on the test. Even though it's a little bit in this lecture, right? We talked about it last week anyway. Even though it might not specifically be in chapter 9. Some of this is in chapter 10. In any case, we said that we utilize a high atomic number. But now you might understand that better because you have a higher atomic number. That means you have more electrons. That means you have the more possibility of interactions occurring to begin with. Gold, we said, doesn't really work very well, but not because it doesn't have a lot of electrons, because it has a low melting point. You might like get one X-ray and then you're done for the day. You know, you've melted things like a dolly painting. Molybdenum, not so good either, but tungsten's pretty up there. Gold is better, but again, melting point, no good. Well, it's whatever has the highest atomic number that is still a metal. So what are our parameters? We've been talking about them, right? We said kV, we said MA, we said time, and mass is really just MA times time. And they're going to affect how much radiation you end up with. And this is where terms like intensity, quality, and amount of radiation and quantity come into play. You have to know those terms and what they mean. So when it comes to mass, we said mass is MA and time. multiplied. When you change the mass, it will directly, proportionally change the amount of radiation. So if you double the mass, which can be done by either doubling the NA or doubling the time. If you double both, then you're quadrupling. So double one or the other. You will double the amount of radiation. Another way of saying doubling the radiation is doubling the intensity. Another way of saying that is doubling the quantity. So in other words, quantity and intensity are the same thing. Quality, not quantity. Quality is a different thing. Quality is how efficient the beam is, the penetrability of the beam. And that's where KB comes in, right? But KB actually does both. Right? KB will affect intensity and quality. KB will affect quantity, in other words, intensity, and quality. But let's stick with mass for a second. So if I double the time, then I get twice as much intensity. If I tell you, increase your radiation, double it with mass, what would you be doubling? Either the NA or the time. It's probably better to double the NA than the time, because if you double the time and the patient moves, then you get motion, right? But for our purposes in the lab, right, you're putting a phantom down, and if it starts to jiggle, we're having an earthquake or something weird is happening, right? We don't have to worry about the patient moving or fidgeting or having a tremor or anything strange. In the real world, you most likely want to increase your MA and keep your time low. Also, just to mention this again, any combination of NA and time that equals the same mass gives you the same intensity. So for example, I have a particular mass. If I then go and half the time and then double the MA, I'm back where I started. Right? I have the same intensity. That's known as the reciprocity law. It's kind of like the cumulative law in math, right? It's 2 plus 2 is 4, 1 plus 3 is 4. It's still 4. Reciprocity law. See, mass is easy to understand, right? You double the mass, you double the intensity. KV, not as easy to understand. And again, filtration, when we talk about it from the beam perspective, we could say that the filtration is going to reduce the intensity, right? It literally takes photons away from the primary beam. But then it's important to understand that the average energy that's left in that beam goes up. We're taking a quiz next week. I have 65 students or so. I get an average for those 65 students. Let's say I take the 15 lowest grades. Someone's going to get 15. Well, not a 15. That would be really terrible. And I take them out of the average. The average will go up. So the number of test scores goes down, right? But the average energy or average goes up. That's what filtration does. Again, if we use too much filtration, if we use more than 2.5 millimeters of aluminum equivalent, I start to kill good photons. Now, KV, we've already talked about what the P is, so we won't go there. And we've already defined it as being the potential difference that's placed upon the tube so that it gives the energy to those electrons to actually make it into the tungsten atom so we can have those Bremsstrahlung or characteristically produced photons happening. But what does an increase in kV do? Well, it increases penetration. So it's better to use a higher kV than a lower kV, if you have to ask that question. Because after all, if you use a higher kV and it penetrates more of the X-rays that would have gotten stuck in you, even though we're only talking about 1 or 2% overall, we can, have a little bit more going through. But subject contrast mostly comes from the X-rays that get stuck. When you change the kV, not only do you change the quality, and when we say quality, we're talking about how hard the beam is, how much penetrative power the beam has. But changing kV will also change intensity. It will also increase or decrease the number of photons you have. But it's not like mass. Mass, when you double the mass, you get twice as many photons. If you double the kV, you fry the page. kV is exponential. Exponential. If you go up about 15% in kV, I'll come back to the next slide in a second that I skipped. If you go up about 15% in kV, the intensity goes up about 40%.
So it's exponential.
It's exponential. In other words, a little increase in kV gives you a lot more intensity. In fact, this is the way you should think about it. It's called the 15% rule. If you go up approximately 15%, the intensity will double. So you don't have to double the kV to double the intensity. You only have to go up about 15%. So small changes in kV mean a lot. Small changes in mass, not so much. So this is a nice graphic, right? Related to intensity. They both start with an electron, but one starts with 80, you set 80, and the other one is set at 90. How many photons do you create, X-ray photons?
80.
80, and this is just one example. It's not always going to be like this exactly, right? They're just trying to show you that energy level that you set has an effect on how many photons are produced. So in this case, with 80, we only get 4 photons. One nice good one at 69, because that happened to be a characteristic interaction. The other ones are Bremsstrahlung. But 90, 10 kV more, is giving us, instead of 4, it's giving us 6. At the end of the day, it's really only the 69 ones that count anyway, because the other ones are probably going to get absorbed or not make it to, because they're pretty low level. But from a pure physics standpoint, and from what's on the test, a higher kV gives us higher intensity. Right? And overall, if I told you to change your kV in the lab, and I said, you know what, you used like too much exposure, use half the exposure. Your question to me would be like, well, I could either cut the MAS in half, or I could go down in kV by 15%. Not both. As a matter of fact, you have to be careful when you go down in kV, because there's a rule. You have to have a minimum amount of kV to penetrate the part, even though 98% of it gets stuck in you. So I guess we're talking about the 2% that actually makes it through as penetrating. But if you don't even have that, then you have nothing. So if you're ready at a low kV. There's only so low you can go because you risk not penetrating the part. So you have to have at least enough to penetrate the part. So if you're doing an abdomen or lumbar spine, you can't use 50 kV. Even if you jack up the MA and the time as much as it'll go. You'll have this. Woo! And it's all right there. Just there. Didn't really penetrate anything. Right? Not enough to hit the spine and show you what's going on with the spine and be absorbed differentially by the spine and different parts of the spine to give you different shades of gray. Not 50 shades of gray. Lastly, the beam, right? The makeup of the beam, the penetrability of the beam, the hardness of the beam. A lot of ways to talk about the beam. Is affected by the generator. The generator you can't change. You could use this room with one generator and that room with a different generator. You can call up people and buy a new generator, but you can't switch the button and change the generator. A more efficient generator, such as a triple phase or a high frequency generator, will give you more radiation in the same period of time as a less efficient generator. Remember I said that you get about a third of the radiation you set? That's at a single phase. At a triple or high frequency generator, which is more efficient, you get closer to 98, 99% of what you actually set is what you get. So if you set 90 over here, you get 30. If you set 90 kV over here, you get 89 for every single photon. So more photons and stronger photons. Using a triple phase generator or high frequency generator is like using a higher kV without using a higher kV. It's just better at creating photons.
Penetrability is still.
Well, penetrability is going to be much higher with the high frequency generator.
So you have different energies that's coming out of this photon. How much? So with this higher, with three phase, less than 98% is kind of like superficial, and more than 2 or the 1% is actually being penetrated.
So I'm not sure if I got all that, but with the more efficient generator, the kVp that you send gives you a much higher likelihood of getting more photons to be closer to the higher amount that you have set than over here. Now, what that means is if I do a hand and I have an exposure that I know works in a single phase room, I need to use a much lower exposure over here because it's more efficient. If I don't, then I toast the patient. Same hand, same thickness, same atomic stuff. We're going to get into all why one thing absorbs more than another. But assuming it's the same hand, okay? Not the same technique. Okay, I use a much lower exposure in this room with a high frequency generator, and that's due to something known as ripple. I'm not going to get into exactly what ripple is, but the less ripple you have, so ripple down, efficiency up. So very low ripple on the right side here, much higher here. Each one of these is giving you an X-ray, right?
So you're essentially getting good, or it's good enough radiant rest without using that much radiation.
That's right. So lowering the dose to the patient is easier to do when you have a better generator. Better generators cost more money, but they are more and more commonplace now. So how do you know what technique to use? Well, we talk about this near the very end, next year, I think. But there are technique charts. There are special ways of making them, and there's a couple different types of technique charts. But every room should have a technique chart. And sometimes it's broken down in alphabetical order and by part, and then by medium, small, large, which is kind of subjective. But if you have the technique chart, it gives you a head start. Do we have technique charts in our rooms? No. Make your own. So when you come up with a good technique that works, write it down. Share it with other people. Remember, however, that the exposure indicator, that's the number that we've said in the lab has to be between 150 and 250. That's the number that tells us if we've used too much radiation or not enough radiation. Basically, I'm going to sound like a hypocrite in another class. Because technically, right, in that example where all the radiation went to my little belly button and nothing got through, that number only tells you how much radiation was received by the plate or the image receptor. If all of it gets stuck, how are you going to measure the radiation? Other than you kind of know what you started with, but you don't know what you ended with. The exposure indicator is the only number that kind of tells us whether we use too much radiation or not enough. When you had film was nice, at least in this one way. I wouldn't go back to film, but film is nice because how do you know you used too much or too little? When the film came out, it was either too dark or too light. If it was too dark, you could hold it up to a bright light. And they used to have these hot lights. If it was too light, well, then you were S out of luck. Because you couldn't do anything with that, except repeat it. Now we don't have this visual cue. We use a whole bunch of radiation, let's say too much, and the image looks what? Looks good. All that math going on, that image reconstruction, that enhancing thing that pops up in room 2. Makes the image look good when it's done. The amazing thing, when you read up about this, is you can actually use less radiation with digital technology than you used to with film. You can use less. The problem is, the system does a better job at correcting overexposures than correcting underexposures. It's something like it can correct for 50% underexposure, but 400% overexposure. So I did a lecture, my first one ever, a while ago, at CW Post. And I talked about this thing called radiation creep, and a lot of people didn't know about it at the time. Radiation creep was the practice of technologists knowing in their mind that they had a better chance of an image coming out good with an overexposure than an underexposure. So the radiation levels would tend to creep up, thus radiation creep. The reality, like I said, though, is you could actually use less than you did with film. And to this day, most people use more than you can. So your objective is, if you're doing CR work, and the range is between 150 and 250, and the higher the number, the lower the exposure in CR, you want to be at 249, technically, right? Because that would give you, or technically 250, right? That would give you the lowest exposure and still be in range. If it were DR, you would want to be at 150, because there, the higher the number, the higher the radiation. So you want to be at 150 versus 250. But be careful when you're in the lab. because even though in my lab it's a little bit different, positioning and centering and where the central ray is super important. If you take an X-ray and the exposure indicator is not where you like it to be, but then you go in and you change the centering or change the positioning or do anything, now the radiation is going through a slightly different, millimeter by millimeter, slightly different part of the part. It's going to change that number. So if you go in and move things, and how does it happen? Well, I take a new CR cassette, because I'm going to take another exposure. I put the part back on, I center it up again. Am I in the exact same place? Maybe you should take a piece of tape and put a little X on it so you know you're in the same exact place when you take that second exposure. DR is easy, because you don't have to change the plate. You just shoot again if you don't like the number. Right? You see what I'm saying? CR, you have to change the plate. Either that or you leave the plate there and you get a double exposure. That's not good either. So what I mean here is when you're doing your analysis, right, and the numbers change and you're not sure why, a lot of times it's because you moved something very slightly. Also, not huge, but no one exposure is actually the same as the last exposure. It's close. When you measure the radiation, it's usually pretty close. So that's not a big issue. But there is something known as reproducibility. That's not on the test. Right? Eventually, every once in a while, you have to test the machine. When I set a certain mass, do I actually get the amount of radiation that I'm supposed to? Right? And there's testing. All right. Questions? When does class end?
45.
Okay. All right. Questions? No? Yes. There's a whole field of quality control. Actually, it's quality assurance. The test is quality control. So there's a lot of quality control tests that fill into quality QA, quality assurance. No, not 250 MAS. 250 exposure indicator number or S number on the CR system. There are a few. His question, does it vary with every system? Yes. I think AGFA uses an LG number, but they all translate into exposure. Exposure indicator is the generic term. Some manufacturers choose to call it something different. Right? It's kind of like, you have ibuprofen, but you have Advil, and you have Motrin, and it's still all ibuprofen, but one company calls it whatever they call it. How do I recommend studying for the quiz? Okay, so this is what I tell people all the time when they ask me that. I'm not telling you, no. I take my lecture and the PowerPoint, right? And I redo my notes, so I have some good notes. Then I take those notes and I read the textbook. And then I use the textbook to expound, not a huge amount, but a little bit more than what's on your notes. So I'm not saying you have to know every single letter of the book. Use the PowerPoint or whatever presentation and the actual verbal lecture as kind of like a scaffold, right? And then fill in some small little, in other words, add detail to what's already there versus really going into the book with very, very new things. So, 98% of what's here and what I talk about is what's on the test. The book goes into a little bit more detail, and I want you to know that detail, but some little things, that are in the book, you don't need to know. absolutely everything. So I don't know if that helps. Plus, you'll just kind of get used to my test.
So like the excitation just wants to know the anode side, not the one behind them.
Yeah.